I'm very happy to introduce today Carola Wenk, who is at Tulane University. I tried looking up her some blurb in order to discuss her varied and illustrious career, but then I decided that perhaps I should just mention that we've known each other for a while, and it would probably be easier to just let her speak, and I'm just glad to have her speak in our seminar. So go ahead, Carol.
Thank you, Boris. I know we've known each other for a while. I actually convinced Boris at the time to be an external evaluator for my PhD thesis. So it took some convincing, you know, to sort of, but he did the work, and I yeah, really appreciate that. So glad to be here. Thank you so much for having me. And let me share my screen. Okay, can you see that?
I can.
All right. And yeah, so please feel free to ask questions anytime. You can also put them in the chat. If I happen to not notice that you put something in the chat, please somebody remind me, unmute and let me know. So yeah, so the plan for today is to talk about comparing embedded and immersed graphs. So and that is basically spans sort of different areas in the sense. So it was motivated through applications by comparing road networks as the two, as you see a snippet of here. But it sort of goes between, you know, geometry, computational geometry, topology, graph theory, obviously. So there's lots of components to that. All right, the slide has been changing, right, for you guys? You see the next slide?
Yes.
All right, cool. Just making sure. So yeah, so I've been working over the years with lots of collaborators. So recently we've been working on a survey about these distance measures. Hence like a lot of faces. And so thank you everyone for you know, wonderful collaborations that actually have gotten easier to do via Zoom these days. You know, across continents and such. So it's really wonderful to work with everybody. There's some websites over there. I have a related book on map construction algorithms. There's some map comparison in there, map as in roadmap. And of course, some grant support over here. So here's the outline of the talk. So I want to first talk about one-dimensional embedded data, such as curves. That's usually what one thinks about there, but then also embedded and immersed graphs. And then I want to talk about Hausdorff and Fréchet-like distances. So, and I'll go into details of those, and then dive a little bit into computational topology and talk about the local persistent homology distance, as well as local signatures. We'll see what I mean with that. And then finally some other distances, edit distances, shortest path sampling distance, and point sampling distance. All right, so 1D embedded data. So one-dimensional embedded data. So I think of this embedded in some ambient space, usually Euclidean space, and often the plane, but doesn't necessarily have to be the plane. So we have, for example, in terms of applications, there's GPS trajectories, for example. They are curves in well, either in 2D, projected in 2D, or maybe 3D on the terrain. They're protein chains, right? So those are, well, curves in 3D. And just as sort of applications of curves, and we want to compare and or align them in order to find similarities or patterns. So this is what sort of often comes up in practice, that these sort of discrete geometric shapes are actually useful in practice, and people want to compare them to find patterns or similarities. And we can also look at sets of trajectories, for example. So here's a set of trajectories, and you see that one may want to sort of cluster some parts of them together. Yeah, so that's called sub-trajectory clustering. So there, we may not want to cluster all of them together, but sort of find the sort of portions that correspond to each other. Yeah, so that's again finding some similarities or patterns in there. Here's another set of trajectories. If you look at this, it sort of seems to resemble some sort of road network maybe, and yet it does, because these were GPS trajectories from some cars on a road network, and one can even sort of construct a road map here. Here on the right, you see the constructed road map in a darker color, and then sort of a sort of benchmark ground truth road map that's OpenStreetMap in the background. But what I've been talking about so far is curves as one-dimensional sort of embedded data. But we can also talk about things like trees, for example, right? These are also one-dimensional and have lots of applications, such as sort of root networks here, plant morphology, or neurons, for example, or trees, right? And we may want to sort of find patterns and compare them and so on, right? But why stop with trees? Let's go all the way to graphs, right? So graphs, you could just have sort of graphs embedded, say, in the plane. And then you may want to compare them, such as roadmap comparison. And I'll get into that a little more in a moment. But there are other graphs I may want to compare, such as sort of handwritten Chinese characters or other things. And in a way, I like to think of graphs as sort of the most general 1D shape, in a sense. So yeah, so we want to compare such one-dimensional embedded data, and I think of them as geometric shapes. And there are lots of distance measures and algorithms for comparing curves, and some for trees, but not so many for like embedded or what people call geometric graphs, right? Yeah, and I think of graphs as sort of the most general 1D shapes. Okay, so, but before we get into graphs, let's just talk about curves for a moment. So a curve, right, is a continuous map from 0, 1 to say RD, right? Yep, so the image might self-intersect, but that's okay. And then, of course, many different curves can have the same image, right? So, and I can reparameterize curves by just having a map from 0, 1 to 0, 1, a continuous map that I call a reparameterization. Often we may want it to be orientation preserving, so that it maps 0 to 0 and 1 to 1, All right, so those are curves. Now polygonal curves, often in applications, you end up having discrete data. And so you may have sort of a sequence of points that you take as specifying a piecewise linear curve. So you just have a finite number of line segments in between this sort of sequence of points that describes a polygonal curve. But of course, this way I don't have a parameterization. So I would usually then think of its arc length parameterization by default. And in fact, if you think of, so one of my motivations here, these types of GPS trajectories, they are sequences of time-stamped position samples normally, and they might have some other attributes associated with them. But yeah. But now let's get into embedded and immersed graphs. Okay, so graph is just a set of vertices and edges, right? So my motivation comes from things like road networks. Okay, so a road network, you know, is a planar embedded graph, right? So so it comes with an embedding, and I'll focus on undirected graphs, and in fact I'll also focus on simple graphs for now. Yeah, undirected graphs, although you might say, well, a road network, what's the point? Normally that's directed, right? I have directions, streets have directions. True, so one could look at directed edges, right? But that sort of quickly it can get a little complicated of how exactly do you want to specify this. I mean, this is a simple way of thinking about it, just directed edges. But what if I have, you know, I have, well, I could have multi-lane roads, that's another thing, but here I have sort of roads in each direction like this, so I sort of care about the embedding of the different direction of each edge. Actually, if you think about it, if you think especially of highway intersections, you cannot always, along an intersection, you cannot take every possible transition from one edge to another. So often not all of the transitions work. So here is an example how this potentially might look like if one really wants to sort of model road networks precisely along intersections. So this quickly gets kind of complicated. And so for now, I'm just going to focus on undirected graphs, although directed graphs are definitely also interesting.
In the picture on the left, you seem to have one intersection of edges where there's no red dot. So that's allowed?
Haha. I'm not sure if I see that right now, but that is precisely, where is that? That's precisely what I'll get into in a moment.
Okay.
Oh, yes, up there. Right. Sure. Okay, I see. Okay, yeah, this one up here, right?
Yep, that's
yeah, right, yeah. And that is precisely the difference between immersion and embedding. Yes, so, right. I mean, this was honestly an omission over here. I guess I wanted the intersection there for a road network for fun.
Okay.
But I precisely want to get into that right now. So we have a graph that's just combinatorially defined with vertices and edges, right? But I want to also specify an embedding or an immersion. And so for that, it's useful to consider a graph as a topological space, you know, like a one-dimensional simplicial complex. Yeah. And then I can talk about continuous functions. So I think of an embedded graph as having a continuous function from G into RD. Okay, that is not just continuous, but homeomorphic onto its image. Okay, so that's what I think of as an embedded graph. And an immersed graph, here the function phi is only locally homeomorphic onto its image. Okay, so what does that mean? So here are those definitions again, okay? What does that mean? So basically the whole point of these definitions is that each vertex is mapped to a point, and edges are mapped to curves in RD in such a way that the graph structure is maintained. Yeah, that's the purpose. But okay, and a homeomorphism, right, is a continuous bijective map with an also a continuous inverse, right? So what that means is that in an embedding, okay, all the edge curves are non-crossing, or in other words, every crossing is a vertex, versus in an immersion, so the bridges are allowed, so to speak. Yeah, so this sort of thing, which is not a graph vertex, but the edges intersect in the immersion, is allowed. Now, I should note that, by the way, in terms of the immersion, so So in my definition here, this is the sort of topological definition, and it does not need to be smooth like in differential geometry, right? So normally in differential geometry, you assume that it's smooth embedding. Yeah, so so while normally if you think about planar graphs, for example, right? So planar graphs sort of like, question is whether there exists an embedding into the plane, right? And I'm going to look at plane graphs or planar embedded graphs, for example. I mean, if we're talking about the plane right now, but I don't want to limit myself to embedding. So most of the things I'm talking about also work for immersion. So it's more general, basically. Yeah. And the point is that because immersions, you have they're locally homomorphic onto the image. So sort of, right, for every point there is a neighborhood where it's homeomorphic. So it's just like the manifold definition, right? But now for graphs, for one-dimensional things. Well, does that make sense? So I want to be able to allow these sort of bridges in a sense. For computation purposes, I'm going to assume that curves are piecewise linear. Yeah, and I may ignore degree 2 vertices. Okay, what does that mean? So if I have these sort of so edges are represented via curves, right? The curves will be sort of edge curves piecewise linear. So if they're piecewise linear, they might have these additional vertices, degree 2 vertices, which I may want to ignore just because they're just part of the definition of the embedding or immersion of the edge. So, all right. So now immersed graph comparison. So, so given two immersed graphs, we want to compare them. Why? Well, so these here, for example, like these two snippets that I'm showing you, those are literally from two different road networks. Well, two different maps for the same road network. Yeah. So one of them is actually from OpenStreetMap, which is a crowdsourced, a crowdsourcing platform for making maps, and the other one is from a commercial vendor. Okay, so and it's interesting that I mean, you see them in overlay and next to each other, but they you see similarities and differences, and the question is what's right, what's wrong, you know. So yeah, so I somehow want to figure out how similar or different they are. But of course, like, what does it mean to be similar? Good question, right? So that depends on the application. And I mean, the first thing that comes to mind maybe is graph isomorphism, right? But graph isomorphism, well, I'll get into that in a moment, is maybe is a bit sort of too strong of a requirement, because we may want to incorporate some partial matchings, and we may want to allow one-to-many assignments as well. And I should note that here right now, I'm assuming that G and H, so the two graphs, are embedded in the same space and aligned already. So I don't want to sort of shift one around to find like a good alignment or so. Yeah, and so the point of this talk is, you know, I want to define different distances between G and H and study, you know, their properties and computational complexities. And ideally, although points 2 and 3 are sort of harder in a sense, so I want to compute correspondences between portions of G and H. This is actually non-trivial, and to do that efficiently. And part 3 is to consider local distance signatures, heat maps, which are more useful in practice. So not yeah, so on the one hand, I want to talk about sort of mathematical properties of these distances. On the other hand, I want to make sure we have something that can be used in practice. All right, so graph isomorphism. Let's sort of the obvious elephant in the room. Okay, why not just use graph isomorphism, right? Okay, right. So isomorphism, well, an isomorphism is just defined for abstract graphs, right? No embedding to begin with. It's just a bijective map between the vertices such that the edges are mapped to each other as well, right? So of course, that's a wonderful concept. And for planar graphs that can be computed in linear time, you know, this is well known. But again, it may not be as practical for this sort of like comparing data that comes from practice, like such as the road networks, because, you know, we may have some missing parts in there. We may want to sort of map certain things to each other, so that we don't just have a strict one-to-one assignment. So this is just like isomorphism is just like too rigid, too strict of a definition to be really useful in practice. So okay, so subgraph isomorphism is sort of the next thing, right? So isomorphism between G and a subgraph of H, obviously that's NP complete. But yeah, it can be computed in linear time if G has constant complexity and both graphs are planar. So, all right. But again, even that is also not sort of the most useful notion for these sort of embedded graphs that come from data and have some noise to them, and, you know, have by definition something's missing. Yeah, so yeah, here's an example again, right? So isomorphisms are one-to-one matchings, but we may want to allow one-to-many assignments or partial matchings. And yeah, isomorphisms are more or less combinatorial and don't take the embeddings or immersions into account by default. So here's sort of a bit more of a motivation. This is, again, some GPS trajectory data, and different algorithms were applied to construct road maps out of this, out of these sets of trajectories. And on the right, you'll see different road maps. So it's sort of the black ones are the reconstructed ones by different algorithms, and underlying there, the sort of gray one is this OpenStreetMap ground truth map. Let me sort of zoom in a little bit. So you'll see that, I mean, obviously the lower left sort of has some issues there, right? But the other graphs, if you look at the ones in the top row, right? Well, like which ones are correct? Like, how do you want to compare them? So how could I come up with a quality measure to sort of say, you know, like to quantify how good the map construction algorithm was, how good the output is, right? That is the question. And again, the input curves were kind of noisy, right? That's the point. Yeah, so how can one measure the quality of constructed maps? Well, so surprisingly, there is actually no applicable ground truth map. That sounds weird that I say this. Like, why is that? I mean, there's professional maps, you know, I was drawing this sort of light gray map in the background. Like, why can't we use that? Yes, we can, but they don't cover the same area that was covered by the input trajectories. So they don't cover the same details as the given input set of trajectories. Plus, the whole point might be that you want to use the trajectories to update the map. So there might be sort of some new features or some missing features and so on, like new roads or closed roads. You know, that's sort of exactly what you might want to sort of find with that. But yeah, so anyways, the point is, wouldn't it be nice if we were able to compare two immersed graphs nicely? Yep, that is the plan. So, so now I want to talk about a couple different distance measures we can consider. And I want to start with Hausdorff and Fréchet-like distances, meaning Fréchet distances and variations of them. Okay, let's start with Hausdorff distance, right? So the Hausdorff distance for compact sets A and B is defined as follows. So here I first start with the directed Hausdorff distance, right? So I fix a point A and look at the nearest neighbor in B, and I do this for all points in A and maximize over them, right? And then I would get for this example over here, that sort of green segment would, the length of that green segment would be the directed Hausdorff distance from B to A, and the length of the red segment, the directed Hausdorff distance from A to B. Obviously, this is not symmetric, but you can make it symmetric by defining the undirected Hausdorff distance as the max of both. Okay, so far so good. And of course, we can apply this to graphs. Oh yeah, and this can be computed in polynomial time in the plane, for example, and n log n time. Yeah, when we compare to graphs, apply to graphs, I mean, we can use it. It's just that it literally only compares the geometry, but not the topology at all, in the sense that sort of connectivity is entirely lost here, right? So these two graphs on the right, where the red graph has two connected components, they have small Hausdorff distance, but we may want them to have larger distance, right? But of course, as a good thing, the directed Hausdorff distance allows for partial comparison of one graph. That's nice. And also the Hausdorff distance is a metric on the set of compact subsets. Okay, so talking about metrics, here, just so one thing that we can study for our distances is, you know, whether they are metrics or what other type of distance function they are, meaning which of the metric properties they fulfill if they don't fulfill all of them. So this is just sort of a metric. So metric fulfills like all four of these properties. We'll say a distance is directed if it does not fulfill symmetry. And then there are various combinations of those properties that have different names, such as a pseudometric, which does not fulfill separability. So yeah, we'll see examples of those. And yeah, and the directed Hausdorff distance in this sort of terminology is a directed pseudometric. So fulfills 1, 2, and 4, and then not 2. Okay. So the Fréchet distance is another distance which is traditionally defined for curves, although we'll get to using it for graphs in a moment. So here's the definition, and it basically ranges over all continuous, it minimizes over all continuous monotone increasing reparametrization. So the usual way to think about this is, or the illustration is, to have a man walking on one of the two curves, those are my input curves right now, and a dog on the other, and they're allowed to, and they hold each other at a leash, and they're allowed to move forward continuously, not backwards. And you look at the leash length, and the Fréchet distance is the minimal possible sort of retractable leash length that you need for that. Yeah. And it can be computed using this notion of a free space diagram, well, decided using a notion of the free space diagrams for given epsilon. We can define this free space, which is essentially you have the parameter spaces of your two curves on the x-axis and the y-axis, and then a point in there is white if the corresponding points on the curves have distance of most epsilon, and it's black if the distances are larger than epsilon. Yeah, and the free space in one cell is a cropped ellipse. Yeah, and there are cells because we have piecewise linear curves. And then a monotone path encodes reparametrizations of f and g. yeah, a monotone path in this sort of product space here. And if that path lies entirely inside the white free space, then the Frechet distance is almost epsilon. And it can be computed using dynamic programming in, quadratic time, sort of as follows, by literally propagating which points on the boundary are reachable with a monotone path from the lower left corner. So you just kind of propagate reachability like this. It's very sort of standard dynamic programming, and then trace back the path. Yay. So that's the Frechet distance. Now we can also define the weak Frechet distance, which is which just looks for any continuous path in the free space, not necessarily monotone path. And then we have that the Hausdorff distance is bounded from above by the weak Frechet distance, bounded from above by the Frechet distance, just because we keep minimizing over I guess, fewer things as we go from left to right over here. All right, and then we can do, with the Frechet distance, we can do some fun things or some nice generalizations. So we can do what's called map matching. It's kind of a misnomer, but that's how it's called. So the setting here is I have one graph and a curve and an epsilon, and I want to find a path in the graph such that the Frechet distance is at most epsilon. Map matching, and for that we can just compute the free space diagram, between the curve and the entire graph. So of course that looks a little more complicated, and I did not actually put in all the actual free space in there, so it's just the product space here. But you can basically use dynamic programming to also find such a path. So it's just a simple generalization. Oh yeah, good question about inf versus why inf not min. I mean, this is a great question. Where is it? It is, so let me see. So that's the question, why do we have an infimum over here, right? Versus a minimum. Well, the thing is that I'm looking at these alpha and beta are these reparameterizations, right? Which are functions from 0, 1 to 0, 1. But look at this curve over here. This sort of curve here sort of the man would stand still while the dog on the other side is walking, and this is not a function necessarily. That's why, an infimum. So yeah. All right. Okay. So now, okay. So in more general terms, yeah. So the Frechet distance can be defined, or actually was originally defined by Maurice Frechet for two oriented manifolds. Okay. So so here I'm going to sort of phrase this in terms of immersions also. So if A and B are two oriented manifolds, and I have them immersed in RD, then I can define the Frechet distance like this, where alpha ranges over all orientation preserving homeomorphisms. Yeah, and this definition actually applies to curves as well. Yeah. So this is the most general definition in the sense, just sort of look at orientation preserving homeomorphisms. And now we know that the Frechet distance is a pseudometric. So that means that separability is not fulfilled, because sort of shapes with different parameterizations can have distance 0. Yeah, but of course we can make it into a metric if we just sort of take equivalence classes and say everything with distance 0 is in the same equivalence class, right? And yeah, but it was originally defined for oriented manifolds, but can be generalized even further, such as for graphs. So how do we generalize the Frechet distance to immersed graphs? So I have G and H, my immersed graphs, and so I can, in principle, apply the Frechet distance definition on those two maps, phi G and phi, and phi H. That's second one should be phi H. But the question is sort of, what does it mean to be orientation preserving? So, I mean, so one option is to sort of drop the orientation preserving requirement and just sort of have homeomorphisms. Yeah. Something to sort of keep in mind. But for graphs, actually an equivalent definition, so we don't have to sort of talk in terms of homeomorphisms. We can also think about graph isomorphisms. So if I have graph isomorphisms and the corresponding edge mappings, right, then I can literally just sort of minimize over all possible edge mappings there and take the max over all edges, and then look at the Frechet distance between each edge and the image or the mapped edge. Yeah. Okay. So, and obviously sort of this definition here, this is graph isomorphism, hard to compute, but it can be computed in polynomial time for trees and for graphs of bounded tree width. So yeah, so I think it's interesting to literally kind of just apply the Frechet distance definition to graphs. And for planar graphs, we can sort of talk about having an orientation, right, by looking at rotation systems of the vertices, right? And we can actually enumerate orientation preserving isomorphisms in polynomial time. For planar connected graphs, we can do that. Yeah.
Carola, may I ask a question?
Sure.
So when you say isomorphisms, but are you looking for the largest common isomorphic subgraph?
Right. I mean, you're totally right. So this is more the, I mean, this is not the best definition or the best distance I want to use, right? Because that's really restrictive and just talks about isomorphisms again, which I sort of said is not the right thing to do, right? Yeah, you're right. Like this one is just sort of really based on isomorphisms. It's just sort of one way to just like directly generalize the Frechet distance.
Thank you.
But I'll get to more things in a moment. Yeah. Mm-hmm. Okay, so let's get to some other distances. Exactly. So here is a path-based distance. So as we said, because like just, I mean, this is sort of a nice mathematically, I mean, it's nice if we can essentially directly apply the Frechet distance definition to graphs, but it's not really that useful. Yeah? So here's another distance, a path-based distance. So this one is essentially the directed Hausdorff distance on path sets. So we represent G and H using sets of paths. The question is, what sets of paths? We can use different sets of paths. And then just compute the directed Hausdorff distance on it, where as the underlying distance metric, or the point-based distance, is now the Frechet distance between those paths, right? And this asymmetry of the definition might actually be desirable if G is a reconstructed map and H is a ground truth map. So ideally, sort of if pi G and pi H are the set of all paths in G, I mean, that's kind of too many to compute, but mathematically I can think about this, right? Then it's a directed pseudometric just because it's a directed Hausdorff distance, essentially. And interestingly, this part here is map matching problem. So we can actually compute this efficiently. So for a given PG, like one path, I can find the path in the other graph that's close, so efficiently. Yeah, but overall, we don't really know how to compute this distance. We know how to approximate it in sort of a special case where we don't have degree 3 vertices and vertices are well separated. So this is a bit of a funny special case, but in that case, we can just look at paths of link length 3 and then stitch sort of the mappings together. So yeah, I just wanted to throw this out as like one potentially interesting distance, but there's more sort of useful ones later. Here is one, the traversal distance. So here the idea is that we represent the two graphs using curves, using traversals. So I look at graph G as a full traversal, so it needs to be continuous and surjective. And for H, I just have partial traversals. And then I compute, this infinite momentum maximum. So it's kind of Frechet-like. Yeah. So here's an example of what this does. So for graphs G and H, right? So we're basically looking at traversals that look something like this, right? So I represent my graph using curves like this and compute the distance between them. Yeah. So this will have small traversal distance. Yeah. But clearly it's a directed distance. And it can be computed in polynomial time using free space diagram. It's directed. And it coincides with the weak Frechet distance when G and H are polynomial curves. Let me talk about another type of generalization or variant of Frechet distance, which we call the strong and weak graph distances. So here, the idea is instead of using this very strict isomorphism or continuous, homeomorphism is this sort of, as a mapping for the Frechet distance, we weaken this and say, well, let's just look at continuous map, which we sort of call a graph mapping here, which is sort of maps vertices to any point on H. It doesn't have to be a vertex, can be in the interior of an edge, and it sends edges to simple paths in H. And the strong graph distance is then a sort of similar definition to the Frechet distance via isomorphisms. It's just that we have these graph mappings now in here. So this is how it's weakened. Yeah. And the weak distance, just if we use the weak Frechet distance in there. And here we have sort of properties, sort of how the traversal and weak graph distance and strong graph distance relate to each other. And sadly, this distance is NP hard to decide in general, but it can be computed in polynomial time for trees. And the weak distance can be computed in polynomial time for planar embedded graphs. So let me show you some examples how these distances sort of behave. So here, if I look at the traversal distance right now, this is similar to the example we had before. So we just sort of walk around here. So I can find these two traversals that have a small distance. So hence I have a small traversal distance. Yeah. But if I look at the graph distance, so the graph distance maps vertices from graph G1 to graph G2, right? So the blue one onto the blue one, you know, and maps these vertices onto each other. So all color coded here. Yeah. And now, but I'm only mapping vertices from G1 to G2. So it's very asymmetric here. So now the issue is that, and now I'm supposed to map each edge to a path in the other graph. So if I take this red edge over here, I have to map it to a path from between the blue and the red vertices in G2. So I have to map it to this path. So I get a large graph distance. Similarly, H1 and H2 over here, they're going to have a small traversal distance because I can just walk around like this. Yeah. But they have a large graph distance because if I take a look at this red edge, I have to walk all the way around over here, right? And the ones on the right, though, the two graphs there on the right have both small distances. now another sort of generalization of the Fréchet distance to graphs is this contour tree distance. And this was defined actually for contour trees, and it was used to compute the Fréchet distance for surfaces. Okay, but you can sort of generalize it to at least to connected immersed graphs. We're still sort of working on what the sort of most general generalization of this is. But let's think about having two connected immersed graphs. And so the contour tree distance is defined as this, where you take the infimum over these special correspondences between G and H. And so the correspondence has to be connected, or all points in the correspondence has to be connected set. And for each, well, and there's these other two conditions, 2 and 3, which basically enforce monotonicity. So let me show you using the example of two curves. I mean, of course, I want to use this for graphs, but for two curves, I like to think of the free space diagram for this, because that's precisely what the correspondence sort of is. It's a subset of the product space, right? And so what condition 2 means is that the set, so if I look at x times h, so for where x is a point in G and times h, right? So this would be that sort of green vertical line over here, right? So I want that the set tau intersected with that line is non-empty and connected. So it's in a sense monotone, yeah, for curves. And similarly for y, that the sort of along the blue horizontal line, the set is connected. So for curves, this definition really boils down to precisely the Fréchet distance definition. So I just think it's a beautiful generalization from the sort of free space based interpretation of the Fréchet distance for curves to more complex objects such as trees or graphs. Yeah, so this is, I think, a beautiful, more general definition. Yeah, but so it is a metric, which is good, but sadly it's NP complete to decide already for trees. So yeah, and it is, and it seems to correspond, we're still working on that, to a symmetric version of the strong or weak graph distances. Yeah. So I think that this contour tree distance is actually sort of hard to find. It's hidden in a paper with the title entitled "Real Valued Surfaces," but it has this beautiful distance definition in there. So yeah. So that was my all the Fréchet-like distances. So now I wanted to go sort of quickly over some other distances, but the question is, so Boris, like, how much time do I have? -2 minutes? Does it matter?
We usually go at least until 3.
Oh, okay, cool. All right. So okay. So then yeah. So here is now a different kind of distance that's sort of rooted in topology, right? Okay. So here a sort of very quick excursion into computational topology, persistent homology, right? So here the goal is to develop these topological descriptors to analyze point set shapes, right? And so it looks like these sort of sets of point sets contains 2 cycles, but how do we know? Or we sort of thicken the points, and sort of at some point we have some cycles, but at some point these cycles disappear. So that's why one uses persistent homology to basically look at these, well, they end up being sublevel sets of the distance function to the point cloud. We look at these different thickenings really, and check which holes persist longer. So we look at the persistence of these topological features. So yeah, so this is sort of just an overview. So the growing union of balls just sort of gives us nested topological spaces, so a filtration, right? And so for each topological space, I can have a homology class, which are groups, really. I have homology classes, which are groups, and which I can represent using bases, and then from that I can define persistent homology classes or groups because of the nesting behavior. So I can basically, this allows me to track these features through the different topological spaces, basically through the filtration. So what we get from this, the whole point of this is that we get these persistence diagrams where we sort of track the thickenings over time, over the filtration. And then I have this parameter R, the size of the radius right now of the balls in this example. And I look at the birth-death pairs for these topological features. So for example, these two sort of holes that we see here correspond to these sort of two points that are higher up over here. So I get these persistence diagrams, which are this topological descriptor of the point set. And what we're going to, and then when I have two persistence diagrams, I can compare them using the bottleneck distance. So what we're doing now is we're thickening graphs. Same idea, we just sort of take the embedded graphs. So this one works only for embedded graphs. We're taking the embedded graphs and thickening them in a local neighborhood. So I look at a local neighborhood, hence these sort of disks over here, and thicken each graph in there, and compute the persistence diagram for each graph in like a local neighborhood. And then I can compute the bottleneck distance between the persistence diagrams. So that gives me a local signature because I computed this locally. But I can also integrate over the locations of my disk, the centers, and over the radius, and then that gives me a metric. So that's sort of very topological. But what's interesting is that we can use this sort of locally and define these sort of heat maps over here. So if we just, or look at these heat maps that we get by just computing this bottleneck distance locally for many different locations where the centers of our balls are right on the edges of the one graph. And you see that, so red is larger distance and yellow is a smaller distance. So you see that this distance really captures the changes in topology, sort of where sort of some intersections are missing. It sort of has the red higher distance. So I think that is really nice. Yeah, and you can apply these local signature idea for different distances as well, but the local homology distance kind of work best for this example here. All right, let me speed through a few other distances. So there's other distances as well. One is an edit distance. I won't go into details, but you can basically define geometric edit operations that are proportional to edge lengths, where the costs are proportional to edge lengths. And this was originally used to compare Chinese characters. And the way this geometric edit distance was defined, it's a metric, but NP hard to compute. So not that useful in practice, sadly, because of the NP hardness. Then there's also some sampling-based distances, so shortest path sampling distance, sort of compute, like start with some seed pair of points, compute shortest paths more or less between those points in one graph, in another graph, compute the Frechet distance, and do something with a set of distances you get from that. So that's sort of something that's useful in practice, but you can't really define mathematical properties that easily for that. And here's another distance that's sort of used a lot in practice, the point sampling distance. And so here you have a local neighborhood, and you basically just sample the one connected component of each graph in that neighborhood with equally distant points. And then you give yourself a parameter tau, and you try to find a bipartite matching where points are allowed to be matched if they have distance at most tau. So they're matched, and some of them are unmatched. And then you can sort of compute precision and recall for this and F-score. So the nice thing is that this sort of identifies points that are matched and points that are not matched. So that is the nice thing about it. It can also be used as a local distance signature, but of course it doesn't really, there's no theoretical foundation for this, you know, but it's practical. And the good thing is that it provides a matching, a one-to-one matching between a subset of points in G and in H. So you see the pink lines over here give you the matching. But of course the question is, what is a good matching? So the pink matching here looks way too nice compared to what I said, we're doing a maximum bipartite matching. So that is not an arbitrary bipartite matching. That was a nicer matching that's trying to use nearest neighbors. And yeah, and another question is something we're currently working on. Can one define this continuously and compute or approximate it efficiently? Yep, so as a conclusion, we've seen a lot of distances for immersed graphs. And, you know, questions, are they useful in practice? You know, we have noisy input, we care about runtime, so if things are NP complete, that's not that useful probably. And what are their mathematical properties? So, you know, can talk about the metric spaces, topological properties, what about these sort of, are the metric balls in these spaces? If they're metrics, are they connected? Things like that. We're looking at that currently. And we would like to compute correspondence or mapping between the two graphs efficiently, but several of the distances don't even compute such correspondences. So this is sort of hard. And an application of that is to merge multiple road networks together. This is, if you have different road network data and they all look a little different, how do you merge them together? This is actually something sort of map making companies are actively looking at right now, and they don't really know how to do it. And yeah, point 3 and 4, of course, it would be nice to be able to optimize this under transformations like translations, rigid motions. And these local signatures are kind of a really nice practical aspect, so that we don't just get like one number back, like the distance between this graph is 84 meters between these two graphs. It's not really useful, but it's more useful to know where are the large distances.